Hi, everyone, and welcome. My name is Aaron Smith, the CEO of the Energy and Environmental Building Alliance. I'm joined as always by Nancy Bakeman. I know we were just talking to Doug. We're all looking forward to seeing you virtually or in person at the EBA Summit coming up in Denver, September the 14th. But today we're really pleased to have the third in a series with Doug Terry. This is from his series From Bleeding Edge to Leading Edge, A Builder's Guide to Net Zero Homes. This is actually part two of the House as a System, a holistic approach. So incredible information in part one and part two. Me personally, this is my favorite series that I've been through. If you're looking to build net zero, Doug has so much knowledge that he can bring to bear and really advance you. So you don't have to go through the bleeding edge. You can go right to the leading edge. We're really proud, Nancy and I, to represent all of you with the Energy and Environmental Building Alliance. We've got over 50,000 members across North America, really around the world, 70 different countries today, builders, their stakeholders, and really it's the early adopters and innovators like Doug Terry Holmes that are driving sustainable transformation of the home building industry. So Doug, so great to have you here. And I think we're excited for part three and even more excited for part four.
Yeah. Well, listen, today I slipped in some additional information right at the very end that I don't think you guys know about. So I'm pretty excited about that.
All right.
We're gonna jump right in though, and thanks for having me again. Just really digging it. And Aaron, I love our dialogue that's been going back and forth over the last couple of sessions. So keep firing at me. I'll try and stay on pace.
Okay. You're excused from pace. This is incredible information, and we'll keep it very interactive for everybody. As always, you put your questions in the chat, put them in the Q&A. I'll present them to Doug, but I think we're going to start off with a poll.
Yeah, we just want to find out where people are coming from here. So what's your occupation? We got a choice here: builder, architect, designer, energy rater, trade contractor, manufacturer, government, or other.
And if you do check other, put in the
I'm
chat.
sorry, this wasn't in the list of questions I received, so we don't have this one as a poll.
Okay, back up.
Sorry about that.
Go ahead and just put in the chat for everybody who you are and what you do. That'll be great. That'll give us a good overview. I'll try to capture them all. We got an energy rater, got builders, quite a few builders. And chat's a little slower, so let's move on. All
right, we'll keep rocking. So just like I said the other week, just like NASCAR, we'll put our foot on the gas and go real fast, right?
That's right. Keep turning
a little bit, yeah, unless they're doing the road course. A little bit about me, President Doug Terry Holmes. I'm past president of Ontario Home Builders Association. For a few more weeks, I'm still HBA's technical chair, member of CHBA and Net Zero and Technical Research Councils. 2019 CHBA Member of the Year, and same year I was inducted into the Air Quality Hall of Fame. And for fun, I like to go and do humanitarian missions every once in a while. So this is me on our first mission down to Puerto Rico. And really relevant, today I was discussing with the Barrie home builders up here in Ontario, their issues with the tornadoes that ripped through Barrie a few weeks back, and our work that we're doing with Institute for Catastrophic Loss Reduction in the insurance industry to try and keep roofs on. And, Aaron, in the old days, which would be like last week, everybody thought about, you want to hold the roof up, right? And really what it's all about is we've got to hold the roof down. So doing some really cool stuff there.
Those of you that didn't view session 2, go back. I think, Doug, you walked through how to lay out roof sheathing to protect against catastrophic tear off. And I thought it was one of the best things I'd learned. Really incredible.
Yeah. So these details, I call it the low hanging fruit, but for about $600 US, you should be able to make your home a lot more resilient, which is kind of cool, right?
Yeah, absolutely.
We're actually about to start a new pilot with Western to look at even further detailing. And again, the point is to try and to do it in a cost-effective manner, right? Because if we get to the point where nobody can buy our homes because they can't afford them, then that's not helping the situation either, right?
But and I like that you had found us instead of using the hurricane straps to go with that screw system.
Yeah.
Truss. I mean, simple change, faster to do, more cost effective to do, but still providing resilience for that home. It's a great tip.
Yeah, and we'd be happy to share the research out of Western, because when they were comparing the H.2.5A hurricane clip versus the 6-inch screw that they studied, the screw was pretty much the same, if not slightly better performance. They both failed under the test because you take the test until they fail. But it was remarkable how close
Yeah.
the two were, and it's way faster to use the screw.
Yeah.
But I'm thinking long term here. This is really, folks, why we need to be doing it. You all got to help me out here and make sure we got a planet left for my grandbaby Corbin. I want him to have some place to grow up when he's, hopefully he'll get to my age and be able to have grandkids, right?
Yeah.
Okay, so we're going to go through agenda and objectives for the day. We're going to look at basement walls, or as I say, the strange case of Jekyll and Hyde. Windows, human versus machine design. And then we're going to look at HVAC systems, high performance HVAC, and we're going to look at 4 different strategies you got to deal with. One's heating, obviously, depending on your climate, of course. One's cooling, one's ventilation, and one's humidity. So we also have to look at what I call evolving thinking. And so we're going to do a deeper dive on this towards the end of the session today, but we're going to look at foam versus low carbon options. How do we manage that? There's also the wall calculator I shared last week. It's got over 16,000 wall runs in it. So there's something for everybody. Just because I showed a wall with foam doesn't mean you can't do one with, say, mineral wool rigid insulation as well. There's lots of options there. So our current thinking is evolving. We're working with a company here in Canada called Building Knowledge. Their principal, Gord Cook, is partner in construction instruction down here in the States for you. We're also working with the Endeavor Center, and what we're looking at is our carbon calculator that we're testing. And Aaron, you'll be happy to know that that's the slides I've added. We're going to show a little bit of results today.
Fantastic.
And so then, really quick little builder carbon challenge. What's on your walls? What are you doing to try and reduce your carbon footprint? Because it's not just what's in your walls, it can also be what's on your walls. So as you know, I've said it a few times, I represent a company called Grafenstone, and we have a product that not only has a zero VOC component to it, and I mean like much more stringent zero VOC because it's from Europe, but also products that absorb CO2, which I think is really cool. Because if we're going to have to paint our walls, wouldn't it be good if the paint we're putting on our walls is also helping to reduce our CO2 considerations? The other part is that when we look at paints that are zero VOC, what we don't realize is that still permits products like formaldehyde, or chemicals, I should say, like formaldehyde, or the other one is MI. It's a really long name. I can't pronounce it very well. It's also a preservative. It was actually used originally also in cosmetics for women. Isn't that nice? You put something on your skin that makes you have a reaction. So they don't typically do that much anymore. But we are tracking it. We're concerned about it, and we're trying to make sure we're not putting products into our homes that are going to make our clients sick. So we've been using Grafenstone quite well for a couple of years, and I do really recommend for folks, if they've got customers with allergens or that sort of thing, asthma, they really need to be looking at what they're putting on their walls. One really cool thing is that Eva's addressing this with that new program that you've got with Dr. John and Gord Cook that you're doing.
Yeah.
I think that's a cool partnership, man.
Oh, it's great. If you're really looking at a healthier home, please take a look at, we have the Healthier Homes Awareness for Building Professionals course on the EBA Academy. This is one of the first attempts to bring a medical doctor together with Gord Cook, who's one of the EBA certified trainers, and really talk about how do you not, remember we used to face greenwashing, Doug? We didn't want to greenwash. Well, we don't want to health wash. Dr. McCune really helps you get to what's the most important part of listening to the customer and addressing their needs around asthma, allergies, or coronavirus even.
Yes, exactly. I think it's great work that's being done there, and we're really happy to be involved with it as well. So more good things to come, I think, on that front. Okay, so everybody knows this guy, right? Dr. Jekyll and Mr. Hyde. In Canada here, we do a crazy thing. We put poly on our basement walls.
Inside?
Inside, yes. And so that's why I like to bring up Dr. Jekyll and Mr. Hyde, because I think that's a perfect analogy for describing how basement walls work when you got concrete on the outside and you put poly on the inside and expect it to work. So we don't do that anymore, and I'll walk you through it. So the thing is when you look at it, basement walls are subject to the same forces, but they have a split personality, and it becomes really more visible when you have an unfinished basement. In other words, the best thing you can do is finish your basement, because then you can't see the problem, except for now you've put the problem away and it's still there and it's going to make people sick, right? So that's why I call the basement wall the strange case of Jekyll and Hyde. In the summertime, and I'm assuming that most builders have seen this. It could be, you know, in the southern states, climate-wise, if you were to be dumb enough to do this, you've got the concrete is going to cook under the sun, and that's going to push the moisture in, right? That's just how you've got this inward migration of moisture happening. And then it runs into a condensing surface, or we call that poly here. And when you do that, you've created what I call that poop sandwich, right? Because the water's got no place to go. You're not allowing a drying path. And we always want to make sure that we're providing a drying path whenever we're building a wall assembly so that we can get water out of the wall. And so what happens is a lot of times builders will come along and they'll cut the poly, right? Because they're being forced to put it on the walls. They'll cut the poly, and then you know what happens? The wall dries, right? Except for now there's winter time. And so in the wintertime, the wall flips. That's the Jekyll Hyde part. And now you've got your moisture migration is migrating outwards in the wintertime. So you've got this warm, moist area in the house, and now it's hitting a cold concrete wall. And guess what? It condenses, right? Mm-hmm. And when it condenses, you know what happens? Well, it freezes. The worst is when it freezes. So it freezes on this concrete wall, and then you get that phone call. And I hate that phone call. My basement's leaking. No, it's not. It's outward bound vapor migration. The wall's condensed, water's condensed on the wall, and now the weather's warmed up, and the concrete has warmed, and now the freeze lens of the ice on the wall has thawed, and now you're getting cooling on your floor. Imagine having that conversation. What do you think the client thinks you, Aaron?
You're just trying to talk them out of something that.
Yeah, it's not fun, man.
Yeah.
And the same thing happens in the summertime. I've got my basement's leaking. I've got all this water on my poly. Well, no, it's because we're doing a dumb thing in our code, really. So the important thing to remember is this, and you know, if you've been through a building science course, you've heard this one before. Heat goes from hot to cold, moisture goes from wet to dry. But what's really important to remember is energy is in constant motion, and there's two basic types of energy movement that we need to deal with. The first, as I said, is heat that's going to migrate from hot to cold, which most people think is hot air rising or the stack effect, but that's not technically what's happening. It's going hot to cold, right? So the hot air is down below, the cold air is up high, and that's why it's rising. Because you can have heat going hot to cold sideways as well, or downward. You ever stood on a cold basement floor before? That's kind of heat going hot to cold, and that's what it's going to pull the energy out of your feet. So since heat moves from hot to cold, you also lose heat down through the basement floor, like I just said. That's when your feet get cold, even though the air itself might be warm because the basement floor is cooler. This situation is actually worsened with full height basement insulation, because now you've got the cold air is migrating down around the foundation and underneath the floor. So the floor can actually get colder, especially the walls being insulated. That floor can get colder because you've got more insulation on the walls. The other thing is this effect can cause drafts, especially around poorly sealed windows, doors, and outlets. So for reducing heat loss and increasing comfort, it's not just about better insulation. It's also, as I've said before, about better air leakage detailing, right? And then there's moisture, which migrates from wet to dry. And this occurs principally in two ways. In the summertime, like I said, you've got the moisture trying to get into the home because it's really hot and humid outside and it's cool and dry inside. And then in the wintertime, it flips. So we have to try and deal with all of that when we're designing a basement wall if we're going to make it work. So if you're doing a crawl space, you don't really have to worry about this as much. You'll still have the same effect, but it won't be something that people are spending time there, so they won't complain about it, you see. So it could still happen, but they're not complaining. So there's two strategies that we look at for our basements. The first one is reduce air movement through the wall, And the second one is enable moisture to leave the wall. So we want to effectively build a more durable wall, right? So there's two easy options to resolving this, and that's using off-the-shelf products. One is stop air and vapor from migrating in the winter, and two, allow vapor to migrate out in the summer. So basically acknowledging that the condition happens, right? So we developed a wall called the Optimum basement wall. This is maybe 11 or so years ago now. We worked with rock wool, which was originally rock sole insulation, and Chris Timmis at George Brown College there. And a young lady, actually, Miyoko Okawa, was part of the research team. And ironically, in a couple of weeks' time, she's joining our team as our head of research and innovation. So we're pretty excited about getting to work with her on a full-time basis. But effectively, the original case study, there it is, 2013. We put a comfort board up against the concrete wall, and then we put the idea here, the four principles, was limit the ability for water to enter the wall. The second one was use materials that won't trap moisture. So I never use pink insulation or fiberglass insulation in a basement wall assembly because I don't think it's the right product for down there. The third one is
Doug, we're looking at the inside of the wall here, right?
This is the inside of the wall. So this is inside the home itself, right? This is not an exterior insulation detail. We've done exterior insulation as well. This specific one is what we're currently doing.
Okay.
And then you got to create drying paths for the moisture migration right out of the wall. So one of the things about the air barrier is we're making not the concrete be the air barrier, but what we're doing is we're bringing the air barrier to the inside of that wall assembly, right? And by doing that, then it's going to block the migration from inside out in the wintertime. And that's really important. But the drying path piece, that's where we've seen that problem with the poly on our walls. And what we did is we worked with a company called Certainteed and used a product of theirs called Smart Membrane. So that was a proprietary product, but there's others on the market now. And effectively what they do is they will act like a vapor barrier in the wintertime to keep more moisture from migrating into that wall. But then in the summertime, they open up almost like a Gore-Tex coat and allow moisture to migrate out of the wall. So we don't get that moisture buildup into the wall assembly. And since I've been doing that we actually developed that wall before we did the pilot. This pilot was the study of it. We found that we've virtually never gotten a phone call about our basements. One time, one guy, and you know what he did? It was summertime and the sun was just blaring down on this house. And he decides he's going to water his lawn in the middle of the heat of the day with all this sun energy bearing down onto this foundation. And he's got the water just lapping on the foundation. And all of a sudden he's calling me saying, my basement's leaking. And I'm like, how about you take your sprinkler and get it off your foundation and the problem's going to go away. Because he was creating so much vapor drive. It was overwhelming the system we designed, right? You know, the problem is, Aaron, we still got to put clients in these houses. And so we have to educate them or just give it a good college try. Yeah. So what we're doing now, this is our more current methodology, is 1.5 inch of rigid insulation against the wall. And then we put our concrete slab goes in over top of the spray foam. And we're using roughly just under 2 inches of closed cell spray foam, right?
Doug, just a quick question here on this assembly. We had a presentation by the spray foam folks, and they were talking about this approach of the closed cell spray foam on the floor instead of putting down a 2 inch, 1.5 inch or 2 inch of rigid.
Yeah.
What's been your experience on the cost benefit of rigid versus spray foam there?
I found that the spray foam, when you factored in labor, was probably a few pennies less for a better seal.
Great.
In fact, when we were using the rigid, my buddy who's a building inspector, you've heard me talking about him a little bit. He used to take his own roll of tape, so when it cracked, that he could fix it for me.
Okay, because every time you step on it, you get a chance of cracking it, right?
Pretty much, yeah. So the sprayed foam just seems to work better.
Well, is it
Um,
too that the gravel that you put down or that class 5 or whatever you put down too, you
Yep.
don't need to smooth it quite as well because the spray foam will make up for some of those gaps.
That's another labor saving right there,
Right,
dude.
right.
Yeah.
Okay.
Yeah, because otherwise you gotta like spread it out so uniformly, because if you've got any voids in there, then you're as they're stepping on it to crack. But here's another thing you got to be careful of as well, though. And some guys will say we should put poly underneath to really deal with your radon detail. We're going to talk about radon in a second. But you got to make sure that the concrete guys do not have a pitchfork, because you see it slows down the curing process by having the vapor barrier. It's a vapor barrier basically underneath the floor, so it's only got inward upward drying, right? You lose the downward outward drying potential for that concrete floor that's got a lot of moisture. It's got to bleed off, right? And so what they would do in the old days is they would go and they'd poke holes in the poly. If you put poly down, it's like, you're killing me because you just ruined my detail and the whole point of why they did it in the first place. So you do have to kind of keep your eye on those boys and make sure that they're not.
So you're not putting the poly down. You're using the closed cell in place of the poly and the rigid on the floor.
That's right.
Got it.
Now, as we start, well, okay, I'm going to get ahead of myself. So let me flick a slide through. So why did we want to deal with this? I'm not going to spend a lot of time on the radon piece, because I think in the States you're quite farther advanced than we are in Canada in the radon piece. But it's the long-term exposure to the daughters of radon, which is the polonium. It's like that spy that was killed in England. They killed him by polonium poisoning. So that's effectively what we're talking about is polonium, because it's not actually the radon that kills you. It's the breaking down to the polonium particles, right? And so long-term exposure, it's the second leading cause of lung cancer after smoking, right? And so that's what we're really worried about. And just for reference here, where I am in Southern Ontario here, down just south of London, we're in a fairly high zone, right? So we do have to do a better job about it. And so we felt that detail of spray foam on the floor was pretty slick, right? We think we're pretty smart, you know what I'm saying?
Mm-hmm.
And so here's a really cool detail from Wall-Tite. Nice BASF 2-pound spray foam, works great. We've had some excellent success with that. And just in case people are wondering about it, I've got the link I can share as well. So we've got a thermal break around our windows. That's pretty cool, because we're actually still doing right now a set in place window. We've got full height 2x6 studs that we've got the 1.5 inch of foam in behind, and you can see we're actually foaming the belt of our header. So the same time they come in and they blow the floor, they do the header as well. That header detail right there, it's worth about 1 air change per hour by just doing that one piece right there. So it's well worth considering. So
I like the approach, Doug, because you're having the guys foam the floor and foam the rim at the same time, right?
Yeah, and there's some guys that will actually foam the wall as well. We don't do that because we've got our own reasons, right? But this works quite well. Then you pour the floor, you stand your stud wall up against it. Bob's your uncle, you're off and running, right?
Yeah. Quick
So
question for you.
Yeah, go ahead.
You're showing that Tyvek house wrap continuous air barrier through the header. So
Yeah.
are you carrying that down over this, down the siding, over the sill plate, underneath, and tucking it into the basement and then grabbing it?
Yeah, because then when you stand your sill poly up, your bottom plate poly up, then you can connect it and make it one continuous air vapor barrier.
Got it.
So the top half of this would be smart membrane. The bottom half of it would be poly, right? Now, when I met with the lady from Certainty that flew over from France to see me, she said, well, you really should be going full height with the smart membrane. And I said, yes, I know, but it'll cost me 4 times as much. So instead of it, being an extra $50, it's an extra $200 a house. And so we don't, because we think we can get away with it. And the research bared her out. She was right, but it works well enough that it can make it work. But if you want to, go full Mac Daddy, you go top to bottom with the smart membrane.
So you're doing, to say if you're doing smart membrane at the top, because that's where you're going to see water potentially, and not.
Yeah, basically, Aaron, it's because that's the part that's above the soil. And
Right.
so it's got the greatest vapor drive happening,
That's right.
especially in the summertime. Down
Yeah,
below
makes sense.
soil, it doesn't, but there's still moisture underneath in the bottom half of the wall. It doesn't build up as badly.
Yeah.
Typically where the buildup is in the top half, and then it'll migrate downward.
Yeah.
But if you allow a drying path out, it won't build up, right?
Yep. And just talk to me about that thermal break window detail. You're doing is that a 1 inch?
Inch and a half.
Okay.
So we actually put a 2x4 buck into the opening. So you've
Yep.
got your opening in the concrete, and then we drop another further 2x4 buck on the outside of the main one.
Yep.
And then as we pull that whole assembly out, you've got a space to put 1.5 inches of rigid insulation as a spacer there. Otherwise, what happens is you've got the concrete directly exposed to your finishing trim wood, and you tend to get rot happening fairly quickly there because there's so much vapor drive happening through that assembly.
Got it.
So this creates a thermal break. It works really, really well.
Nice.
Yeah, it's a neat detail if you're doing a set in place window as opposed to a corner in place.
It just extends the width of the buck, right?
Yeah.
Yeah. Okay. Makes sense. Thank you.
Yeah. You're just making the buck about 3.5 inches by 1.5 inches. So a 2x4 on the inside. And then that way, when you set your window in place, because the window has a built-in thermal break as well, it gives you a thermal break to protect the wood effectively. Or, if you're drywalling it, that's even worse. It'll rot even faster if you're drywalling it. Right?
Nice. Thank you.
It's kind of a cool detail, eh?
Yeah.
So this detail works really well right up until you start to consider the carbon footprint, right? So we're hesitant to give up on it because as a production builder, we're going to do maybe 200 homes over the next year or close to it. When you start getting into that level of production and you have to maintain your pacing, this is something that's working really well. So when we start to look at the carbon footprint piece, okay, what else can we trade out, right? But really great news happened back in January where it's now an HFO blowing agent, not an HFC blowing agent.
That's right.
So because of that, it's dramatically reduced the intensity of carbon when using foam, right?
That's right. So Doug, most of the global warming potential of the blowing agents came from the blowing agent was the carbon potential.
Yeah, because most of the rest of it's basically air, right?
Yeah, most of the rest of it's fairly inert, but it's that blowing agent was causing some of the bad global warming. So now
Yes, for sure.
moving from HFCs to HFOs, you go from a high global warming potential to almost 0 or 1 on global warming potential, right?
I would say it's not the greatest culprit in the house at this point.
That's right.
It's definitely improved the situation for certain, right?
Great.
So I guess hopefully we've got a question or two here. The first one is, what type of foundation do you install? Full height basement, crawl space, slab on grade, or other? Because there could be somebody doing wood frame basements, right?
Or all of the above, right?
Yeah.
Yeah. Great. Nancy, can you put the poll up, please? Okay, you should see the questions there. Go ahead and click your answer. Hopefully you're still awake at home.
Well, I'm doing okay. I'm just getting warmed up here, so I'm ready to keep rocking.
And maybe a quick question. What's the difference between the rigid foam inside the foundation wall versus the outside? And what do you consider to be the best practice? That is from our good friend, Tim O'Brien in Milwaukee.
The excavator.
So what you're saying is, well, the backfill is going to destroy your exterior insulation, right?
Well, no, a good excavator, he's not going to destroy the insulation, but
Yeah.
Exterior is a great approach. And hey, the nice thing about the Grafenstone stuff is I've got mortars that I can use for putting stucco on the outside that'll help to absorb carbon for 1.5 years while it's curing. So yeah, exterior is a great approach. I think, isn't it in Minnesota, you can't do interior insulation, you have to do exterior?
Oh, I knew there'd be a Minnesota building code question for me today.
Yeah. I think it is Minnesota, but I don't know. I'm a fan of more insulation, really.
Tim, maybe Wisconsin can be a proxy for us here today, and you can chat us back if what the Wisconsin code allows.
But the big reason why they were doing that is because they didn't want to have the vapor bloom issue that I was just describing that we've resolved, right?
Right.
So, either can work. You just have to think through the science a little bit in order to get it to work. I think we have one other
poll question.
Another one.
So just on that last one, 100% of people were doing full height basements.
Good. Good. This is good to hear.
Yeah.
Have you incorporated radon mitigation measures in your standard specifications?
Okay, what I can tell you here, Doug, is code in Minnesota is you must do passive radon mitigation system that's planned for active with room for the fan in the attic and a plug for the fan in the attic, just in case.
The only thing I don't like about the fan in the attic and the plug for the fan in the attic is the maintenance piece.
Underpressurization.
Yeah, I don't know. We're permitted to put it out the sidewall here in Ontario, and I don't mind that detail.
You can also put it out the sidewall. Yeah. Nancy, next quiz, please. Or poll.
I think that was it. I think I'm just looking for the poll results here.
I'm sorry, it won't allow me to do the radon mitigation question. I don't know why it's giving me an error message.
Okay, well, we'll just keep going. Maybe some folks will throw it in the
think about that
in the chat.
Tim O'Brien says cold wall condenses inside without insulation outside. That is what I am told by our friends at Construction Instruction and Justin Wilson.
There you go. There you go. Yeah, it will. That's one of the reasons why we wanted to have the drying paths through, right?
Yeah.
But yeah, exterior insulation, it's a great, or the ICF actually, there is a detail using ICF that actually further reduces the carbon footprint. And that's something we're going to be playing with over the next couple of years to see where that leads us, right?
Yeah.
I think part of the reason why it reduces carbon footprint is because you're using less concrete. Windows. I'm back on Windows.
This is lesson 3 of Windows, right?
Yeah, because everybody's getting it wrong. So that's why I keep pounding away at it.
Right.
So I often say Windows, human versus machine. You know what? Software doesn't complain about comfort, but humans do. I have never, ever had a phone call from an energy design software complaining that it was too hot or too cold in their house. Right? So why do we design for software? Right? So there's 3 different kinds of energy loss. We all know this, right? Radiant gain loss. We can control that with low solar heat gain coefficient. Convection loss, I feel a draft. Well, I think we want to eliminate the draft, and that comes back to air tightness. And then conduction loss is the cold surface pulling energy away from the warm air. And that's the reason why you want to use triple glazed windows, right? So unfortunately here in Canada, most of the windows that we use, they are favoring energy rating. We have this crazy thing called energy rating. You guys don't have to deal with that, right? And effectively what they're saying, well, we're a heating climate, so we want windows that gain heat, and we're going to give you more points for windows that gain heat. So here's some, and I actually got an exemption put into the Ontario Building Code that we're now trying to get put into the National Code that effectively says, okay, Natural Resources Canada, they administer the Energy Star program in Canada for windows and for houses and what have you. On the left is a window that's a Canada zones 1, 2, and 3. So you can pretty much use that anywhere in Canada. But on a little bit, it says energy, see where it says energy performance rating, and then it's got a 34 here. Right. That's your energy rating, okay? And so why that's a concern is that's a high heat gain window, okay? Now you imagine I'm building a super tight home that's highly insulated, and I have windows facing west, and I allow those windows to gain heat. Does it make sense to run the air conditioner in January? No, but on some walls you would have to in order to balance out the house. On the right, up at the very top, here's an energy rating. It's only a 22, okay? This actually does not comply. It says this window with this glazing option does not qualify. So technically, I'm not allowed to use this window for building in Ontario, okay? But when we look at the U factor, do you guys use 0.22? I think that's what you would do, right?
Yeah.
And then it's got a 1.25 is the metric equivalent, right? So I come over to the U value, same thing. And the window that's got the high energy rating, Aaron's got a 1.71. It's a crummy window, right?
Hmm.
Why? Because this guy over here on the right's got a 0.17 on the solar heat gain coefficient. It's designed to block heat gain. Whereas the one on the left, it has a 0.54. You're effectively putting a furnace that's not controlled into that house if you use that window.
And Doug, I remember your guidance from earlier sessions was always below a 0.3 for solar heat gain coefficient.
Even get it under a 0.3 for certain.
Yep.
Get your U value under 1.4. So your metric on that, I can't do the equivalent equation. I think it's under a 0.26 or something like that. But your building science guy can tell you about this if you really push them on it.
Yeah.
Unfortunately, not all building science, your energy advisors, not all of them are really clued in on this specific issue. So what you really want to do, and I'm talking even the northern state climates, because remember, when you're in Minnesota, you're farther north than I am, right?
Yeah.
So I'm down what we call the banana belt, right down near Detroit. So with what you're looking at,
that's where we go on winter vacation.
Yeah, there you go. There you go. So when we're looking at this, we really want to get that number down, right? And so that's what we would do. And I would suggest that in the northern climates, you should still be considering it if you're building a net zero home, because in a net zero home, you just can't gain heat that you can't control, right? It'll blow up your cooling loads. I think you're using manual J down there. It'll blow up your cooling load. Your sizing gets huge, and your performance goes out the window. So it's really, really important. And the other thing is once you've selected what your window specification is in order to control this, don't let anybody change it on you,
right?
Because that just makes the problem worse.
I think what you're bringing up, Doug, is a really important concept around net zero, which is that passive strategies always beat active strategies, and that windows are a key component of a passive strategy to control loads in the house. Then you do your active strategy, which is your HVAC, based on that correct sizing. Because otherwise, I love what you always say is the guy comes to your house and puts his thumb up and says, oh, 2.5 tons. Well, that is an active energy penalty for the next 22 years in that house.
Yeah. Yeah. And there's ways around it. And we're going to get into mechanical sizing in a little bit, but there's ways around it. And that's why I just harp on windows so much, because they have such impact. Heating and cooling, right? The view is so lovely, but I can't sit beside my room there because it's so hot I can't be in there, or I'm in there and I'm freezing because I've got such a bad draft. It doesn't have to be like this, and I'm not talking a lot of expense in order to manage that and get it under control. So it's really about looking at our details and about what we're selecting, right? Anyway, why is that important? Well, remember we talked about Goldilocks. I think that was in the first session, right? So I'm still on about Goldilocks. We want to design for Goldilocks, not the cyborgs. Cyborgs don't live in our homes. People do, right? That machine that'll spit out your formula to say you should be using this type of window because of that and the other, they're getting it wrong. I don't think the algorithms are right. But a person will tell you they're too hot, right? So let's make sure we're designing for Goldilocks, and then we're going to have fewer calls. And that's really what we're talking about. Is part of being conservation is to reverse engineer problems out of the build so you don't get that phone call, because the call is really expensive, right?
Right. So
mechanicals, we are now into mechanicals, and there's basically 4 systems that we have to consider depending on your climate zone, region, et cetera, et cetera. But we have to heat the home, we have to cool the home, we need to ventilate it, right? And then you probably need to do some humidity management, because when we're building a giant plastic bag and sticking people inside of it, when they breathe in, breathe out, even with ventilation strategies, there's reasons why the system might not completely keep up. So we're going to go through a bit of that today as well. So heating and cooling. I don't know, have you ever seen this dance before? I'm hot, I'm cold, I'm hot, I'm cold, right? So that is because of furnace sizing, right? And so what happens is, and I had the worst situation we had, and this is actually where I really started to understand we had a problem here, is I had my furnace installer. This is way before I started doing our own takeoffs and everything like that. He put in a single stage 75,000 BTU furnace into a home that had a 30,000 BTU heat loss. I couldn't for the life of me balance that house because it was short cycling so bad. And what that short cycling is, it's an oscillation profile of the temperature going up and down and up and down. And so the temperature would go up, it'd overshoot the thermostat, and then it would crash down over a period of time. Well, you're hot and you're cold if you're where the furnace is kicking in air in and out. But if you happen to be in an extremity in the home, you could be cold the entire time because you're just not getting enough air into that room in the amount of time that the furnace is running. So overshooting causes an oscillation cycle, and that's that too hot, too cold dance that we want to get away from. So that's when we started working with a company called Dson. And if we're going to have gas in our homes, then it's really kind of important that we start to really look at sizing correctly. And when I've got home loads that are maybe 24, 25, 26,000 BTUs, and I'm not talking tiny homes here, Aaron, we're talking, a 1,500 square foot bungalow to a 2,000, 2,200 square foot two-story. These are decent sized homes.
Right.
We couldn't find anything out there wherever to hit our loads. So we partnered with Dson, and we did the pilot project with them for North America to bring this specific furnace to market. And what we loved about it was that it had between a 12 and a 30,000 BTU delivery. It's about the size of a large suitcase. And we found it was a really great alternative to using water-based heat, because when you're doing water-based heat and you hit a hard water situation, you know what happens? You blow your water heater in about 4 months. Mm-hmm. So not really cool. And the other thing is that the water-based heat that we've been accustomed to using, it's a bit of a cooler temperature. It's not really as, folks don't like it as well. And I know I had it in my home for about 12 years, and eventually I did swap out to a Dson system. The first thing my wife said is, I can't believe that this house recovered. It was like, as they're doing it, they put in the furnace, and it was late November, it was really cold, and we didn't have any heat in the house for the day. And the house got cold because they had the doors in and open. And then it recovered in about an hour. She was shocked, right? And then after a couple of weeks, she says, I can't believe how comfortable this is. We ended up getting rid of our duvet because the home was comfortable. And this was an Energy Star home we built in 2008 or something like that. So we've been in there for quite a while.
Now, Doug, is this Dson unit? I know they make some great heat pumps, and
yeah.
Is this a heat pump unit backed by natural gas, or what are we looking at here?
No, I'm going to walk you through all of this. Okay.
Okay. Got it. Thanks.
This was the first pilot we did. So this was the North America pilot for Dson, doing what's called the right size furnace. Okay. So when we did the right size furnace, then we started to think about, well, we probably need to look at our cooling load. So here's the challenge with the cooling load. Typical air conditioners, they're normally oversized to the needs of the home because of that, using the thumb method, right? And then again, that leads to the short cycling of the unit and lots of short run times over the cooling period. If you talk to a guy like Gord, he's going to say, the furnace or the air conditioner, it really needs to run about 13, 14 minutes before it starts to have much of a dehumidification effect. Mm-hmm. And so the tendency is you're going to turn the thermostat down because you're not satisfied. You're not cool, right? Because there's still humidity in the air. And then you turn it down and it runs again, but it doesn't run. And you just effectively keep chasing cold and clammy. You're getting colder and you're not getting rid of the moisture because it's not running long enough until you're quite cold and it's running for a long time because you've turned it down so much. So it's really important, again, to right size. Part of the reason we want to really, again, come back to the windows about right sizing is that helps to reduce our air conditioner size. Because when the air conditioner is sized for all this extra heat gain that's not controlled, then most of the time you're going to be oversized for what the loads actually are, and you're going to have problems, right? Although you'll still have that 1 or 2 rooms that's too hot, right? So right size cooling is important. Duct design is being driven by the cooling loads, to be honest with you. Mm-hmm. So then we talked to Dson about, well, if you got really great answer on heating, what about cooling? And so we developed this system, which is an air source heat pump technology. It's a mini split, right? Mm-hmm. And so we twinned that, put an A coil into the furnace plenum. And so what we're running now is what I refer to as a dual fuel hybrid heating system. It's hybrid because it's two different sources of heat. You've got a furnace and you've got an air source heat pump. It's dual fuel because it's furnace is gas and then the heat pump's electric. So it's a dual fuel hybrid system, right? But it's really cool because what's enabled us to have happen here now is we've got between 3,000 to 30,000 BTUs of heating, and you just pick a different set point as to when you want to have it switch over. We actually did a pilot with Ryerson University where they created a fuel switching device. So you could have a choice of, well, I want to save cost, so I'll switch when it's the most cost effective. Or if you wanted to reduce your carbon footprint, then you would use the electric for further down in temperature. So the electric, the air source heat pump, it can go down to about -20 and still work. And this isn't a cold climate one.
Doug, just if I can clarify, I think what you're saying is you can choose the outdoor set point at which you start using natural gas and stop using electric based on your environmental consideration or budgetary consideration, right?
So right now what happens is, and yes, you could do that. I would say that it would be the HVAC contractor that's going to set that up. But what we were working on with Dr. Alan Fung at Ryerson was to create one where it would give the ability for the occupant to make the choice depending on which way they wanted to go.
Right.
So that's come out of pilot now, but I don't think they've put it into manufacturing. But it's very cool research. And it was on one of our homes in Strathroy, Ontario, one of our net zero homes actually. Nice. And the idea being is if you had a lot of solar gain that day up in the wintertime, that you could switch over to run that air source heat pump. Really, it's cold day, lots of sunshine. You switch to the solar and you got free electricity. You're running it at almost no cost, right? So it allowed the ability to go back and forth, which was really cool research. Yeah. And I'm hoping at some point that they're going to be able to go from prototype out to actual developed and usable, right? And then duct design. Duct design becomes incredibly important. So before I get into that, and if I've covered it off in here because I can't always remember my slides, think of duct design as kind of like if you take a bowl of water, Aaron, and you want to carry the bowl of water, you can carry a bowl of water fairly well as long as you don't tip it on yourself, right? Now, what happens though when you take that same volume of water and you put it into a colander, right? All the water spills out, right? Because we want to get to the good stuff, the pasta that you're draining, that's going through the colander. You want to get rid of the water then, right? Well, that's typical duct design using SMACTA level C standard design practices. You're looking at around 30 to 35% leakage in your ducts, right? Now, and then you guys go even crazier and you put your ducts up in the attic and you insulate them and you've got this huge footprint in the attic of what you're doing. And so we really wanted to find a better way. So I actually worked with dson and the Abacus lab down in Pittsburgh. Mm-hmm. And we developed the throw device that's shown here up at the top and gave them some pointers on what that throw device needed, how it needed to work. And then they went and created it with a 3D printer and then ultimately got it manufactured. So what we do is what's called smart ducting, right? And that system right there, we've gone from 30% leakage down to about 3% right out of the box. So I have 90% less leakage than a typical, let's try and seal this up duct design, right? Now, Aero Barrier, they've got a great product for houses. Well, their parent company, Aero Seal, they can do your ducts if you're wanting to get your duct size. But it's really important to understand that what we're doing is much smaller. So we've gone from low velocity to mid velocity. I don't need to move near as much air as what every other builder does because I don't have leakage, right? So we can pinpoint exactly where we want the air to go. And then we put best science behind us. And I actually should throw a slide in here at some point that looks at the mix pattern of air in a home when you're using interior wall high throw versus from the floor or from the ceiling. From the floor is just about the best or worst location because it'll go up halfway up the exterior wall and then it peters out and falls down. And you have cold areas or dead zones in the room that aren't really getting exposed to airflow, right? Whereas with the smart ducting, it uses the ceiling almost like a plenum and it blows across the ceiling and it has a much higher mix pattern throughout. It is important. We don't want to be putting it directly over top of where people's heads are and having it blow down on their heads. but this system is much more efficient. Now, this is the Dutson Smart Duct system, but I believe RIA is a company that's got one in the States as well that's doing some really cool work on theirs. And so we're pretty excited about the fact that we're getting options here moving forward with things like smart ducting. The HVAC contractors, what they're going to tell you though is once they get used to it, you know why they really like it, Aaron? Because they're not as sore at the end of the day. This is a lot lighter. It's a smaller carbon footprint, but they're not having to lift huge plenums and trunks above their head all day long. So let me show you a little bit of what I'm talking about here. So when we're looking at this, we're actually building our ducts into, and that's 6-inch round there. That's a supply that's built into a bulkhead that's then feeding the floor above, right? So there's a couple of photos of it and then another one here. So we're able to fit our ducts into the floor joist and then just drop them down. So you want to wash across the wall or across the window, or you want to wash it out towards the window. Your third choice, which is your worst choice, but it still works, is to drop it from the ceiling down. I would do that in a basement situation, basically, is about it. But we've had the odd large open concept 2-story where I've had to do that on the main floor to get it out to the outside of a door, like a patio door, that sort of thing. But we do want to really look at where we're placing our system and what we're using. But when we look at this, this is a beam here, and on each side of the beam is a 6-inch run, and then the return is the rectangular box, right? So we're not using as much tin. It's a smaller profile. We're putting probably about 1/4 of the tin into a home that a typical builder would be. And we don't, so we have smaller bulkheads as well, right? And that's really cool. And so we're considering or suggesting that with smaller duct design systems, that's mid velocity, they're extremely quiet, that maybe we can convince builders to not put stuff like this in the attic, right? Get it inside the home, and then, you know, you don't have the challenges that can happen if a Texas happens, right?
Right.
It's a more durable system. So here's the RIA one. And this one's a little bit different in that this one actually goes
It's a home
all
run.
the way back.
Yeah, it's a
to
home
the-
run system.
Yeah, it's a home run system, right? It's I think a 3-inch round instead of a 2.5-inch round, but certainly it's available in the States, and we're talking to them about doing one of our home systems with it because of the specific home that we're looking at. But the continuous run, it means there's going to be, again, very little duct leakage and really easy and fast to install. In both of these companies' cases, though, the return air is not one that they spend a lot of time on. So you do kind of want to know a little bit about return air, because you're going to have to make sure your designer is picking up where they leave off on the return air side of things. So I've got a couple of really simple principles that I follow as far as return air goes. Above grade, put it up high. Below grade, put it down low, right? The reason is hot air rises and cold air falls. So if it's in the basement, it should be down at the floor to pull air off the floor. If it's really up high, then it's because it's upstairs, right? And then the other thing about return air is, in my mind, critical, because you can do a centralized return and not put it out to the bedrooms. You're going to have to make sure that you've got good jumpers if you're going to do that, to pull air out of those rooms. Because the analogy I give for trying to get people to understand this is, if you think about putting water into a glass and you've filled the glass and you're still trying to put water into it, well, it's just going to spill out and go elsewhere, right? If you happen to drill a hole in the bottom of the glass, you can put water in there forever, because it's just going to keep replacing itself. And that's kind of what I feel about return air, is that it's important. And, you know, there's other guys in the HVAC industry that are way smarter than I am. But I feel that you've got to be able to allow the air to migrate out of the room. So you got to circulate the air. And so it's not just hot air rises, so put them up high, and cold air falls, put them down. But I do like to do the runs right out to the bedrooms to make sure we're getting the air coming out of those rooms. So design loads are also really important, and we'll talk a little bit about that. When we do our designs, we actually, for our unfinished basement, we design the rooms, and then we design the loads for those rooms. So we actually calculated, even though the rooms don't actually exist by the time we hand the house over. But if we're finishing a basement, we're already done, right? One thing for tricks of the trades as well here, it's really important for the sizing. The duct designer, you got to give them the expected heated and cooling loads, and you got to give them your typical air leakage and make sure that they understand what it is they're using. Because if they go to the default, tight home, it's actually higher than what is a net zero home. It's usually around 3, I think, air changes, 3.5 air changes, and net zero, we're under 1, right? So we want to make sure that they understand the inputs. And then again, back to the windows, give them the specifications and make sure that that's what they're inputting, or you're going to have problems, right? So that's going to make a difference in sizing your HVAC system, and right sizing is extremely important for overall performance and for occupant comfort. So for us at CSA F280, it's a really good document. In the States, I believe it's Manual J.
Right.
So I don't know, you remember this movie?
Oh yeah.
Yeah, they're having some fun, right? So they're out there cruising, right? And if you're cruising, you can have a good time and you can maintain your speeds and you're just rolling down the highway, right? Well, these boys that were in the movie The Hangover and they're cruising down the highway, that's basically the same argument for why you want modulation. Because what you want to do is you don't want to get caught in stop and go traffic. You want to be able to have your system run like a car on the highway. Long continuous run times, high ramp up, low ramp down, and you don't want to have that stop and go traffic because it's really a killer on performance. And if you can make it more comfortable, see, he's got happy smiley faces on there. That's what we want our customers to be like, right? We want happy smiley faces, and we can do that if we look at modulation. Now, the mistake when I was working on a change to the Ontario Building Code for getting you call it direct current, we all call it an ECM, I guess, motor, is that I assumed that when I said an ECM or direct current motor, that they would factor in modulation. And then when they wrote the code out, they didn't. And so now there was a bunch of manufacturers that came forward with a direct current motor because that's what I got put in the code, but it wasn't modulating. So it's still single stage. And so you're losing a huge amount of the benefit, right?
Doug, our code is shifting to ECM motors for all. I think that went in effect at least a year ago, if not longer. So you have ECM.
And it's good, right? But you lose the benefits of the ECM if you don't have modulation, right? And so we've had some really tough going with the American furnace manufacturers. They've really not done it. In my mind, they made the furnaces small so they could put more of them on the box, but they didn't drop the BTU loads. And so that's the challenge, is that we wanted to get them smaller, and then we wanted to have modulation, because modulation is really the key to comfort. You've got to be able to have it pick the temperature it needs and have it be able to sit there and not keep blasting and blasting and blasting. So you got this gun going off every 10 minutes and overheating the home and dropping, overheating the home and dropping. We've got to get away from the oscillations. So cruising down the highway, that's what we're looking for, right? All right, so then this is the dual fuel versus hybrid heating, and that's what we're running right now. So we've got the Chinook furnace, which is gas on the one side, and we've got the Dutson Alizé. You put the two together. I've got, like I said, 3 to 30,000 BTUs, and this heating approach, we piloted it for North America, but it would work, Florida, wherever. You need a little bit of heat. The air source heat pump takes it. You need a lot of heat, goes to the furnace. So guys building bigger homes in Tennessee would do quite well with this exact system. So it's important to understand the dual fuel technology, but it's also important to understand this is a transitional technology. This is here because gas is still fairly cost effective, right? But as we start to move more down towards net zero path, well, then you start thinking, if I'm going to put in solar panels, why would I put in gas furnace? So over here on the right is the Dson Supreme electric furnace. They're a leading manufacturer of electric furnaces in North America. They've been doing them for, I don't know, something like 70 years. On the left is our model home where we're trialing this. It's been going quite well. The cost is relatively equal overall to running the gas furnace. And so it's basically the exact same setup, except for it's an electric furnace. And this is where we think we're going to be landing within a couple of years as we're working to reduce our carbon footprint. So this is working on the operational carbon footprint. The smart ducting is working on the embodied carbon footprint by removing the amount of metal that we've got in the building or significantly reducing it. A couple of references here for you, and I can share these links with you, but you can Google them and look for Natural Resources Canada. And we actually were involved with the reports on these, and some of the stuff that they put in there was research that we'd done that they've built into it. The left-hand one, Master Planning and Decision Guide for Natural Gas Mechanical Systems. And then the other one is the Zoning Duct Design Guide. So we don't actually do full zoning on our systems because we found once you really well insulate the home, once you really well air seal the home, and once you deal with your windows, it becomes less of an issue to do zoning, right? And then when you have people that like these, I've got a home, it's a 2-story, and I don't have any walls in my house, aren't I proud? Well, where the hell do you put the system, right? And so that's what we're looking at really, is making sure that we've got all of that covered off. But that's two really good design guides that are available, and they're free, right? You can go online and just download it. So I would recommend it, you know. And part of the reason why I really got involved with the Master Planning and Decision Guide was because builders are, we don't know mechanical systems well enough. And so, you know, we're relying on HVAC contractors that are, like we've said, still using their thumb, and then they're gone when we're having the liability of the client being upset, right? So this is an opportunity for us to teach builders the basic language of mechanical systems so that they have a fighting chance of understanding what it is that they're getting themselves involved with. And any builder that's new and starting out and looking at net zero, this is the type of stuff that they should be reading. Now, I know it's a natural gas mechanical system on the one on the left, but the principles apply if you're using electric or what have you. So don't get caught up on it's gas. We're using the same concepts for HVAC. In fact, we're about to do for Natural Resources Canada some videos about this in a few weeks' time. And, you know, it's hard to say to them, yeah, okay, we're doing it, but we're moving away from gas. But, you know, even Enbridge, the gas utility up here is saying, can we put solar panels on your roof because we can see where it's going, right? Mm-hmm. And so that's a really good segue to Enbridge and some of the stuff that they're doing with looking at geothermal for housing. And they're willing to come in and put in geothermal systems now. This is a pilot we're actually looking at to reduce our greenhouse gas emissions and getting right-sized geothermal systems. And one of the big problems, Aaron, with geothermal systems is they're typically oversized. And so the performance isn't there because they're too big. And that's one of the things that we're working on in the industry, is to get geothermal down in size. Buildings, not as much of a problem because you've got a lot more load that you can deal with. And buildings as well, the nice thing is that you can actually blow off some of that heat and get snow melt for free, right? That's part of week 4 though, so I don't want to blow up my presentation for next week. But there's 2 different types of loop systems. If you're on a farm, you can do a horizontal loop. It's far cheaper than a vertical loop. If you're in a subdivision, you're going vertical and you're probably going down 700 feet. So this is what's called a geo exchange system. And the nice thing about what Enbridge is doing is that their program is going to eliminate the cost for the builders because it bundles the loop together in an affordable monthly service charge. So they're taking all the capital expense and then they're doing a monthly bill. So instead of having a gas bill every month, you're having a BTU bill every month for what they're doing. It's kind of cool. That's why I wanted to share it, to just show that there's options out there besides gas. Where we're betting is on houses is going to be air source heat pump technology with an electric furnace. Where we're betting on buildings is that we're going to geo, but again, we're going to deal with that next week.
Doug, do you talk at all about your water heater selection, or where are you betting for water heater?
Currently, we're using a Rinnai tankless. It's about 196,000 BTUs or something like that. 96,000 BTUs, I think it is. High recovery rate. It's a gas one. Mm-hmm. As we're looking to switch to electric, we're looking at doing an air source heat pump water heater.
Got it. And do you like the one
now in our apartment units though? We're using, like, I think it's a 30-gallon electric because our loads are so low there, and we've got space considerations, right? So yeah, we don't have very big water heaters in our apartment units.
Got it. And for your homes, if you look at that air source water heater, are you looking at one that has the intake outflow? So your air exchanging outside of the building envelope? Are you looking at a split unit like the Sandin unit, or what are your thoughts there?
I think we're probably going to land on having one that you can divert the air out. And so in the wintertime, you don't want to be cooling the basement.
Right.
So divert the air out in the winter, but grab the free cooling in the summer.
Right. Okay.
That's where I think we're going to land. We'll know better in a couple of years. And Aaron, some of this stuff now that we're going to get into between today and next week is, I got this crazy idea, and you want to jump off the bridge with me? I tend to do that. I've done a lot of research and know roughly where I want to go with it, but that's where we think we're going to land on water heaters. Great. Now, I wrote the first guide for Natural Resources Canada on doing geothermal heat for solar water heating, and we made a big play into that for a few years, but there was just very little uptake. There was no incentives whatsoever, and so it really never took off. But it did start our path towards solar overall, and ultimately the solar guide in Canada, which is really quite good, was a result of that initial pilot project that we did for Natural Resources Canada, where we wrote the spec for them.
Great. Nancy,
we're on a.
Want to try this poll?
Yeah.
See if it works.
Again, I'm getting this error message that says another poll has started. So I don't know what the problem is. It won't launch.
Technology is grand, Nancy, right until it doesn't work for you, eh? Maybe we can get a few people to toss it into the chat, Aaron.
Let me try. Did it work?
Tim O'Brien says gas, but moving to hybrid.
Yeah.
It's a really great approach, Tim. The nice thing about it is you're setting your houses up for that ultimate transition over to all electric, right? Yeah. But right now, gas is still reasonably cheap. Although what I'm hearing on the global market is that the LNG or liquid natural gas market is really tightening, and numbers are exploding because there's so many countries now that are trying to get off of coal that it's pushing the LNG market higher. And so we may be facing higher natural gas prices on the home front sooner than what we think, even though there's a lot of fracking still going on.
Doug, what do you think about for, I think you're talking about a key resiliency point for the future homeowner of your houses. But what do you think about making it electric ready? There's some programs and some states and some provinces that want us to have things be electric ready. Are you kind of future proofing for that, or that can always be added at a later date?
Well, when you're doing a dual fuel hybrid, that is electric ready. All you've got to do is swap out your furnace and you're there.
That's right.
So we're suggesting that right now, if gas is still being put into the communities, then that would be, an interim approach, if you will. It's a transitional approach, Aaron, and that's what I'm doing right now. And I would suggest that there's a lot of builders out there that aren't even looking at this. And the concern is that at least by doing an interim approach, you are partially reducing your carbon footprint, and you're setting your occupant up for transition a lot more easily in the future, right?
Yeah.
Effectively, the furnace has to get replaced. You replace it with an electric, and Bob's your uncle, off you go. And we think that that's where it's going to land. Now, next year, though, and we're having a raging internal debate within our company because, we're Southern Ontario. We still have winters here. Our townhomes that we're going to be doing next year, which is our first set of towns, it's going to be like our apartment buildings. They'll be all electric. There will not be gas to those sites because we're not putting gas in there.
Right.
We just don't see the point, right?
Right.
It's the writing's on the wall. It's just a matter of when, right? So that's why I say the ultimate goal is all electric. But a good transitional technology is the dual fuel hybrid system, which enables you to move over fairly easily, right?
Makes sense.
Yeah. The big reason why we're not putting gas in those, because when you start getting into these tighter footprints, it's a couple more penetrations for the water heater, a couple more penetrations for the furnace. Now you got 4 more penetrations. You got to figure out where to put them, right?
Right. Sure.
So it cleans up your building envelope. It cuts down some costs, and so there's just a lot of benefits.
Yeah.
Greg Hussey from Carwood Homes, a quick shout out for him. He's doing a test right now with Panasonic up here in my city, St. Thomas, where they're basically going with mini splits, and they've eliminated the furnace system completely. So that's that's kind of some really cool radical thinking going on there as well. So we're monitoring that, and Panasonic is doing the research with them on it. So it's really cool that we're going to be able to see how that works out over the next year to 2 years on the home that they're doing.
That's great. Well, sorry about the poll. Let's drive on.
Ventilation. Okay, so I kind of like to bring movie analogies in so people will remember what I'm talking about afterwards and not say, what the heck was he talking about? So ventilation is kind of like the Blues Brothers. We got both kinds. We got country and Western. Remember that scene?
That's right. Yeah.
What type of music do you play here, ma'am? Well, we've got both kinds. We've got country and Western. Love that scene. It's one of my favorites out of the movie. One all-time classic movie, right? Belushi and our boy Danny Aykroyd from Kingston, Ontario. So we've got both kinds. We've got windows that open and a fresh air machine. Sam Rashkin loves it when I say fresh air machine. I don't know if it was Gord or Sam that first taught me that, but it's pretty cool. I love using that analogy because it makes it less scary for the customers. Oh, yes, please. I'd love to have a fresh air machine, right? But windows that open are important, and we want to make sure that we provide them for our customers, and we want to encourage them. Whenever you want to have your windows open, by all means, have your windows open. But there's going to be lots of times, like today, it's 31 Celsius. So it's about 90 here right now, right? It's hot and very, very humid. We don't want the windows open today, right? And so that's why we use the fresh air machine. In our particular case, the brand we're using is the Van E. There's other ones out there, but we're using an ERV, or energy recovery ventilator. And for a long time, they weren't really available in Canada because the manufacturers didn't know how to do the cooling or the thaw cycle, right? And so you would have the HVAC contractor, you'd throw in an HRV, heat recovery ventilator. So all ERVs are an HRV. So every ERV is a heat recovery ventilator. HRVs are not an ERV though, because HRVs don't deal with moisture. So an ERV will deal with both heat and wet, right? And so you're going to recover about 70 to 75% of the heat energy, heating and cooling from an ERV, but you'll also get about 50% of the moisture recovery. So that's really important. And what we want to do is we want to basically set it up for the customer to run it on the smart cycle, 20 minutes on, 40 minutes off. And then what we think is really important about that, because we want them to have fresh air. And I always ask the customers, when would you like to have fresh air? And the answer should be all the time. And if they don't say that, then I keep working on them until they get to the answer of being all the time. Windows or ERV, right? But one of the things that we've noticed over the last few years is that you can have a fairly heavy humidity dump in a shower and a bathroom, and that might kind of have a moisture loop effect happening on the ERV, where you're not really pulling as much moisture out of the home as what you want. Now in the wintertime, that's pretty cool because you want to have a little bit more moisture staying in the home. So that's not a bad thing. But in the summer, when you're in extreme humidity events and high heat, it's not maybe the best thing. So over the years, we've started to move for the ERV to being in large volume of air spaces. And then like our 2 stories, the main bath and the ensuite, we spot ventilate that. And basically now we're the ensuite in all of our homes, we spot ventilate it. Get rid of that high humidity load right out of the house because we don't want to keep it. If by chance you want to maintain that humidity load in the home because it's wintertime, then our suggestion is leave the door open after you're done your shower and put your fan on continuous on your furnace and let that just pull the air out of the room gradually to mix it in with the rest. So there's some solutions there, and part of that is teaching our clients how to use our homes better. But our current thinking is that we want to make sure that we've got a couple of spots in the home where we're pulling air out of large volumes of air to really pull the air and mix it through to the home better. And then the return side, we do a simple return into the cold air return of the furnace system. That's how we mix that air back in. So that's a kind of a soup to nuts basic strategy on this. The next bit is, where we are, Aaron, we've got these shoulder seasons. We call them spring and fall. And I remember having a chat with Andy Oding, a friend of mine from Goldilocks, several years ago. He's Gord's partner. And I said, Andy, we're seeing high humidity loading events in spring and fall where, you'd think that the temperature outside would mean that we're pulling in cooler air and we'd get some dehumidification coming from ARV, but they're super loading. We're having high humidity events. And I says, I think it's a sign of the climate change. And he was like, he up and down, Doug, no, that can't be happening. You've got the delta T difference in temperature between outside and inside. You're going to get the benefit of dehumidification. And I says, I'm telling you right now, it's not happening.
Just for example, Doug, today in Minneapolis, it is 73 degrees Fahrenheit and 79% humidity.
Yikes.
Yeah.
Yeah.
That's uncomfortable.
That's tough on a system, right?
That's right.
And so we're asking this thing to try and do magic, and it can't. And then, about 2 years ago, he came back to me and says, Doug, it's anecdotally, you're right. This is happening. We're seeing it with more of the high performance builders are having the same complaint. And so what we're doing now is we think that, the ERV is a really important component of our homes because we have to ventilate and we have to ventilate continuously, right? And that's where I think it's incredibly important that we give our homeowners the tools to be successful with it. But there's 3 times a year where this system is not going to keep up. This is in the northern climates I'm talking about. You've got the high humidity dump load that you're talking about right now today, Aaron, where, what they used to do, the HVAC contractor would say, well, shut your HRV off in the summertime, right? Well, what? You need to live in a plastic bag and don't need fresh air in the summer? How does that make sense?
Not a good idea.
Right. So that's why we switched to an ERV. But it was because they were getting humidity complaints in the home. And so they thought, well, we'll remove the source of the humidity, which is the outside air, right? Well, okay, but now you're threatening their health of their occupant. That doesn't make sense. But then there's also spring and fall where, you might be heating in the morning and cooling in the afternoon. You're not really sure. It's up and down. The house gets confused. It's not sure what it's doing. You've got, it might be, 15 outside, but high humidity event, and you're just not getting enough dehumidification happening. And that's where I think we need to start considering humidity control, right? And so humidity control becomes really important. And Dr. John and Gord do this far better than I do. But I think it's important that we look at optimum relative humidity. And I like the simple graph because it keeps it fairly straightforward. The relative humidity in the blue bars in the center, that's your range. So 40 to 60, roughly speaking, 35 to 55 is a really good range. I would say wintertime in a cold climate, and this assumes a well-insulated home with, it's really important to get into triple glazed windows, right? 35 to 40%. Now, summertime, 50 to 55 is a really great range, right? So that kind of overlaps with what's shown on this here chart, right? So if we can manage our humidity into that level, it's cool. Now, here's the thing though, is it means your home isn't as dry. So that means you don't get the fun of shocking your kids. When you rub your foot on the carpet with your sock and then you shock them and their hair stands up. Well, that doesn't happen as much. So it takes some of the fun out of being in the home because you can't play with your kids that way. But, my daughter would get upset with me, but the grandbaby might think it was a hoot and a half, really. But when we look at the older, drier homes in the wintertime, they may actually still have to add a humidifier. And depending on the modern home and the client and how they're using it, you might want to add a humidifier, especially these really big homes with very few occupants in it. They're not creating as much humidity. It might still over dry a little bit in the wintertime, even using the ERV. Most of our efforts, though, are more on the humidity being too high and how do we manage that excess humidity. So a real quick chart on humidity here. This is maximum relative humidity. There was this guy on the TV years ago, Jan Eeks. He, I think, got replaced by Mike Holmes. But Jan's a great guy. I've met him a few times. We've had a couple of nice chats and shared some research together. But you can see this maximum relative humidity chart. Now, unfortunately, it's in Canadian, so the math is a little bit off here, but 30 degrees Celsius or below, that's really stinking cold, okay?
Yeah,
and
just so by the way, the only thing I know is minus 40 is the same in Celsius and Fahrenheit.
There you go. Well, it's getting there, right? Yeah. So 15, imagine having a house at 15% relative humidity. Well, we used to get that, and it was crazy, right? So that's the maximum indoor relative humidity at 20 degrees Celsius, which is 68 Fahrenheit, right? Mm-hmm. So when it's really cold outside, to avoid that excess humidity on the walls, we have to drop our humidity level in the home. but it's not comfortable. We really don't want to go there. So like I said, I've already stated this. All ERVs are HRVs. HRVs are not ERVs. HRVs can overdry in the winter. HRVs can overwet in the summer. ERVs will work to balance the humidity. So it's important that we consider both heat, latent, and sensible energy in when we're looking at our systems. That's why I'm really a fan of ERVs, but they may not keep up. And so then you have a choice of, do we look at running a dehumidifier in the summer? And if we're going to do that, by all means, the best thing to do is to run it with a hose, set it at 50% relative humidity, run the hose right down to the drain. Because if you think customers are ever going to remember to empty that drain on a regularized basis, they'll pull a fourth of the humidity out of the home that they need to, because they'll forget to empty the drain enough, right? Now, there's the odd science geek that'll remember to do it, but most people won't, right? So I just say, set it at 50%, clear pipe it, call it a day, and move on. But there are some alternative methods, and Ultra Air, who I believe are involved with EVA, have a pretty cool system, and they've got some different options. They've got them that you can actually build it into a stud wall cavity, or you can have a system like this, which connects into your ducting system. So there's some pretty cool options out there. And I think as we get into these higher energy load events or higher humidity load events, our systems, we're probably going to have to go down the path of providing dedicated dehumidification systems for our customers, because the loads are just too hard to control. So that, Aaron, basically wraps up on HVAC. Now we're going to talk carbon again, because we talked carbon session 1.
Mm-hmm.
And so really what we're talking about is the two pieces of carbon that we have to talk about. And why I get concerned about the energy programs across the boards is they look at operational carbon, and basically that's it, if they talk about it at all. It's really about, we're going to conserve energy. And in most cases, the backgrounder information is because we're looking at reducing our carbon footprint. And, yay, us, we've reduced our carbon footprint. But if we're not careful and we don't look at the upfront embodied carbon, we can actually make the situation worse, which is the work that Chris Magwood's doing. Chris is going to be speaking at the conference, and I really recommend folks take his session in, because it's pretty cool what Chris is doing research-wide. So the embodied carbon, that's really the embodied footprint, the carbon footprint of a builder or infrastructure project before it becomes operational. So it's everything up to the operational piece. It also refers to the CO2 produced, maintaining a building and eventually demolishing it, transporting the waste and recycling it. So, when I tore the kid's house apart and had to get rid of some stuff, and it went into the landfill, that was affecting my embodied carbon, right? So that's where, when we're looking at it, why should we build the 100-year home? Because if we're thinking about embodied carbon, we don't want stuff that we're throwing out every 25 to 30 years, and we have to think longer term. Are we going to get there tomorrow? Well, we've got to learn how to do it. And so that's part of what Chris's research is doing. So I'm not going to go crazy on this whole thing here, but I just wanted to kind of give you a bit of a snapshot. So this is, the cradle to gate versus cradle to grave, right? And so operational carbon, which is what we focus on in these energy programs, is really only a snippet of everything that's involved with this. And that's why I say I don't think we're really looking at it the right way, and why I think we need to expand our thinking, our horizons, to be looking at the embodied carbon as well as the operational carbon, and also cradle to grave, the life cycle. So what we're picking, is it more durable? That's why it's important to make a wall that's more durable. That's why we've got to get the water away from the wall and the air away from the wall, because we want the wall to last longer, right? Does that make sense, man?
Yeah. Some of the new thinking too is around, instead of just cradle to grave, it's cradle to cradle. So are we then able to repurpose materials that we've used in one house for its 50 years or 100 years into the next one after that? So the thinking here continues to advance. Lots of excitement here. I also am very much looking forward to Chris Magwood's presentation.
Yeah, he's a really cool guy. Like I said, he's doing some awesome research. But there's also ratings. So when I look at, remember that I said about the Grafenstone paint, they've got products that are actually cradle to cradle gold and silver certified.
Yeah.
And so there is the ability to look at product listings. Absolutely. And look for products that are cradle to cradle certified, which is kind of cool, because that wasn't available even a year or so ago.
Sure.
But I want to just do a little quick dive into a case study. Now, this is new to me. We just got this report, but I wanted to share it with you. So there's a couple pieces in here. Don't ask me too many detailed questions because I'm still learning it. But it's the point is to show the direction. If that makes sense to you. So this is a case study on one of our homes, our North Gate. This home, actually, a version of it was the very first Net Zero of the Year home award for Canadian home builders, which is pretty cool. Not this version, a different version of the house. But if we look at taking that home as our template, and we were to look at, I've got my other thingies in the way here. There we go. Doing it to code with the high UEC or embodied carbon emission, the upfront embodied carbon on it, you're looking at about 198 kilograms of total embodied carbon in this house. Going from a high UEC down to a typical one, you can drop it down to 137. Where we seem to be landing right here, right now, and we've been working on the spec with them over the last several weeks, so this is relatively hot off the presses, is we're down to about 116, and where we're targeting for the next 24 months is we want to get it down to 91. So we think that we can get our emissions down by half of what they would be if we were not doing anything and just building a code built style home with not looking at carbon at all. It's kind of neat, eh?
Yeah.
So it breaks it down, and we're sharing the slide deck, so people are going to see this. It breaks it down by different types. And so you're looking at, say, for example, the high content of cement mix, then looking at an average carbon concrete mix, and then with some with the SCM content, and then going to a high SCM.
Doug, I believe the SCM content in this is like adding fly ash or recycled material to your concrete, right?
Yes, sir.
Yeah.
Yes, that's exactly what we're talking about here.
Yeah.
But I know we are running up on the clock here.
We're okay. I think this is important and worth going through. And I think, Doug, your measurement, I actually went through this with Adam Wright from Building Knowledge Canada this morning. So
Okay.
your metric of 198 kilograms per CO2 equivalent is per square meter of house.
Yeah.
Yeah. So that's the normalized data. They're actually
Per square meter.
square meter. Yeah.
Yeah. It's crazy, eh?
Yeah, we would do square foot here, but it's easy enough to convert.
Times by 9, I think it is, something like that.
Yeah, but I think it's really great because you're able to look at your material selection and then substitute within the tool that's been developed and see what might be a better selection from an overall carbon footprint reduction.
Well, like we said the other week, number one with the bullets, that foundation wall.
Yeah, right.
That's the bright orange right here is your foundation wall. So
Right.
you get that under control, and she drops down pretty quick. Footings and slabs is another piece. So there is an argument to be made about slab on grade, but there's also an argument to be made, I think, about looking at certain types of ICF where you can actually reduce the amount of concrete going in. Concrete's the big evil here, really. It's the worst of all.
I think it's, we were talking with the teams as we all look at carbon footprint and really, if you look at concrete, steel, brick, insulation,
Yeah.
which again, there are good EPDs for these product categories. So you can actually calculate this. You're getting to 80% of the impact of the whole house. Now, where there's not environmental product declaration stay is some of the product categories like HVAC equipment or appliances. But I think over time, those will come and give us a better picture, but it's only going to give us the rest of the picture, which is the additional 15%. So what you're doing here is giving a really good picture of the building. We're still getting operational carbon from appliances or HVAC equipment, but we're not yet counting the embodied carbon of that. But it's a great start. It's a great way to look at what types of different concrete could I use? What types of different foundations could I use? What types of different insulation could I use? And how would I lessen that carbon footprint?
So we're going to be taking this design work in-house probably within the next 6 months because we're going to be ripping all of our homes and we want to start to be able to test, okay, if we use this product, what type of a difference does it make and that sort of thing. So, we're very glad to share our research as we move forward with the industry. In fact, the lady that's going to be doing it, Miyoko, I mentioned her previously. She's also, she does a project report writing. And
Mhm.
so as we're continuing this research, we'll be creating pilot project reporting to be able to share with the industry. So what we're suggesting is Chris is doing phenomenal work, Chris Magwood, but it's more on the custom built side of the equation. And what we want to try and do is really road test his program from a production built standpoint, so we can see if we can't make it a lot more robust. And that's really where we're trying to go with this. A couple more slides to share though. And
Great.
here's a really, really neat one. And so you're looking at your concrete benchmark, and then that's the XPS foam. So remember, there was some of that in the basement as well, and underneath the slab, and et cetera, et cetera. So foam was a huge part of this, right? And then you've got your brick, clay, et cetera. So it drops fairly good. And so they just take you through, okay, if you make those changes that we talked about, how things start to drop down, right? And then so you look at the next one, and concrete really doesn't drop after a certain point. But the siding, you gain quite a bit by going from brick to fiber cement or those thin brick, right?
Right.
So there's some options there. And then the last one is going to the HFO blowing agent. So that coupled with the going with the cellulose or mineral wool insulation, that's actually it's there. It's changed what it was looking at, but it's to pull out to show you where a real drop can happen, and that's by changing your actual insulation values as well.
Yeah.
Although your concrete didn't really alter a whole lot. So the solution there appears to be use less concrete.
Right.
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 So we're going to keep playing with that. And then basically looking at specs. Okay, what's in here? So that's the high UEC amounts in here. So, this has got a 2x6 wall on, say, above grade wall, 16-inch on center, wood framing and siding. It's an R22 fiberglass bat. That's basically what they're showing. And then you're moving it through to, okay, this one here, it's a 2x4, 16-inch on center. And then it's got 1.5 inches of continuous insulation on the outside, et cetera, et cetera. And they just keep running through these specs for you, right? And then, so this is ours. This is what we're doing. R60 in the attic, 2x6 with fiberglass bat, R20 and 1.5 inches of rigid insulation. So it's R7.5. And then what our foundation wall is, and then the basement slab, et cetera. And then where we're proposing to go. And this is our first goal, our stretch goal. This wouldn't be, where we think we're going to be in 5 to 10 years. It's our stretch goal as we really start to wrap our brains around this, right? So that's kind of where we're heading with it. And then this slide's a little bit different because this is kind of getting back to Chris's work. So this does not directly relate to like our best one that we're proposing. This would be long-term best, if you will. We're starting to get into carbon sequestration. So some really great choices to look at. And I'm not suggesting that we're all going to get there tomorrow. We need to, start looking at this. We need to go after the low-hanging fruit, and we need to start bringing this down. Really, what I was trying to do here today, after 2 days, 2 sessions of looking at specs, though, was to say, as you're looking at specs, wouldn't it be cool if we had a calculator tool that we could look at, okay, I did this, I changed my design here, and this was the result in my carbon footprint. That's where we're trying to go with this.
Yeah, I love it. It's fantastic. And of course, Doug's advice is, if you boil this down for simple, if it comes out of the ground, it's good. If you have to mine it.
No, if you grow it, it's
if you
good.
grow it, it's good. If you have to mine it and smelt it and things, it's not so good.
Yeah. Or if you recycle it, it's good too. So
Right.
if you grow it or recycle it, it's good. And if you have to mine it and smelt it, then it's maybe try and cut down on that a little bit. Right. Now, you're also looking at, when you're looking at best UEC, wood windows. Well, wood windows scare me because I grew up in a house with wood windows. I go, far enough back that that's the case. And they're a lot of work. And the concern is if the occupant of the house doesn't maintain them, then are we short cycling our cradle to cradle situation, right? So all of these have to be balanced out with all of the factors that we look about and talk about. So, climate resiliency still got to be part of it. Your indoor air quality still got to be part of it, and your occupant comfort still got to be part of it. So we have to look at all of those things. Water management is still critical, and air tightness is still critical. We can't forget those 2 fundamentals and the 4 principles. But I think it's really cool that we are on the cusp here, the starting point of a journey on carbon, and I'm talking embodied carbon here now, reduction. And I just think it's such an exciting time and opportunity for us as an industry to be able to be out on the leading edge and talking about this and figuring it out, right? And
Amen.
we just got to get a whole lot more people doing it.
That's right.
Nancy, I don't want to throw you under the bus or anything, but we're down to our last question here. So actually, no, it's not questions, it's our takeaways. You're all good.
I was just gonna say, this isn't one of
Holy-
the polls.
No, I'm just messing with you. Not on
Scared
purpose. I
me.
screwed up.
Hmm.
So the takeaways are basement walls, understanding the strange case of Jekyll and Hyde, windows designed for humans, not cyborgs, high performance HVAC, right sizing does matter, and then understanding loads and impacts for your heating, your cooling, your ventilation, and your humidity. And so, you know what, I think we're a couple minutes over, but I had a really fun time today, man. It was great. Thank you to Eva for allowing me to come out and go off for an hour and a half. And Aaron, I love our dialogue back and forth. It's always great fun, man.
Oh, it's great.
Yeah.
Learned a ton, and we'll look forward to seeing everyone in part 4 next week.
Outstanding. Thank you so much.
Thanks, Doug.